All right, our video for this one will be on the Pythagorean theorem, which I'm sure most of y'all already have memorized and probably already know how to work pretty well. But I am going to give you a couple of really important extra tips and hints that you may not know already. So let's start out with the theorem itself. And like I said, most of y'all already have this memorized. A squared plus B squared equals C squared. I don't know. It's just something about it that students don't forget. One thing I do want to make sure you understand, though, is when to use it. So we use it typically when we have a right triangle and know two sides of the right triangle, and we're looking for the third. Now, there is one exception to this. You can use this in a right isosceles triangle if you only know one of the sides. But any other kind of triangle, right scaling, right, it's the only other one, right scaling, you have to know two sides. So if you only know one side and it's not a right isosceles triangle, then you'll have to go find a trigonometry or another method. Let's look at the picture and talk about the labeling of the triangle. And one thing I would do an essay about this is, a lot of students will say, I know that C is the hypotenuse because it's the longest, but that's true. But it's also because it's across from the biggest angle. Remember, when you think about triangles and the fact that they add to 180, if this is 90, these two other angles are going to have to be less than 90. So this is across from, which means it never touches 90. That's how you identify it. It never touches your finger if you put your finger on 90. And that's the hypotenuse. And it is going to be the longest side. And that's important as you work your problems to keep a check on whether you're getting it right or wrong. But it's because it's across from the biggest angle. So this is the hypotenuse, and the other things we just call the legs of the triangle. All right. When we get numbers on here and we start putting numbers into the formula, it doesn't matter which one we put in for A or B, but you do have to make sure C goes on in the proper place in the formula. So let's look at an example. Okay, so if I look at this example and I think about where things are going into the formula, the biggest thing about the Pythagorean theorem that you have to be careful about is if they give you a number for the hypotenuse, the formula itself turns into subtraction problem if you put the things in the right place. We're going to call this A and B. So A squared plus B squared equals C squared. I know this means 3 times 3, so that's 9, and 5 times 5, that's 25. But because the 9 needs to be moved away from where this letter is, I do have to subtract it. And we need that to happen anyway, because I know my answer needs to be smaller than 5 for this to all work out. And if we added, we would get a number way bigger than 5. So x squared is 16. And of course, we don't want x squared. We want what x is. So we can undo the second power by taking the square root. And what you do on one side, you have to do on the other side. Now, when you're in some of your higher math, algebra 2, college algebra, the answer here is plus and minus 4. But because we're dealing with things that are distances, we know we only have positive values. So we're only going to take the positive answer of this problem. This is what I call the 3, 4, 5 triangle. It is one of the triangles that I like my students to have memorized, because you're going to see a lot of triangles that are multiples. I call them families of the 3, 4 triangle. In fact, let me go ahead and show you that next. So if I have another triangle that's, let's just say, I'm going to turn it around a different way. I don't want you to think these things have to be oriented one way. Turn it upside down. You still need to be able to identify that this across from, you can draw out from the right angle to help you identify the hypotenuse. This is a hypotenuse. let's say we're looking for the hypotenuse this time. And let's go ahead and say this is, I don't know, 12, and this is 16. Well, if you think about it, and you think about the numbers of the 3, 4, 5 triangle, this is 4 times as much. So let me just draw another 3, 4 triangle, 3, 4, 5 triangle right here. So when I compare this to the 3, 4, 5 triangle, 3 times 4 is 12. And 4 times 4 is 16. Well, that means that 5 times 4 is going to be my answer of 20. And you really can not even have to work the Pythagorean theorem if you use this 3, 4, 5 triangle. There are some other ones. And by the way, when you have a triangle, we'll talk about this in another example. If you have all of these numbers that are whole numbers, we do call that what we call a Pythagorean triple. So this would be called a Pythagorean triple. Let's do the work of it though, just to see the work of it. So a squared plus b squared, we don't know c, or we didn't a minute ago. 12 times 12 is 144. You can use your calculator if you need. 16 times 16 is 256. Again, if you need a calculator for that, pick up your calculator. That should be 400. And then let me just show you the square root button in case you haven't seen the square root button on this calculator. So let me zoom in so you can see this just a little bit. So the square root button is right by the 7, but you have to hit the second button first. And then you come down here to this button right here, and you see what it does? It puts the square root symbol right there. And then we can hit in the 400. And there's my answer of 20. And we already knew that from the thinking a minute ago. Don't forget, you always have to take the square root because we don't want, let me scoot that up where you can see this. Let me zoom back out where you can see this whole problem. So we don't want what x squared is. We want what x is. And remember, it does need to be bigger than 12 and 16 because 20 is my hypotenuse. X is my hypotenuse. So I know my answer needs to be bigger than those two numbers. Okay, let's do another example. Let's take this triangle. Let's say the hypotenuse is 9, one of the legs is 7, and I want to know the other leg. All right, so we're gonna put the 9, where it belongs. I always tell the students to label the hypotenuse. You don't have to label the legs, but always label the hypotenuse to make sure it's in the right place in the formula. 7 squared plus x squared, 49, plus x squared is 81. We're solving it by subtraction, kind of like the first one. And you can get your calculator out if you need it. 81 minus 49 is 32. So we need the square root of 32. All right, that is 5.7 if you round to the 10th, which most of the times they're going to like you to round to the 10th. Again, think about your answer. Is your answer less than 9? Because it has to be, and it is. Now, this would not be a Pythagorean triple because we have a whole number, but a decimal here. So if they ask you, is this a triple, this 5.7 counts it out. Another important thing I want you to understand is they could sometimes leave this as a simplified radical. Let me just quickly show you about that. This breaks into, sorry, not 8 and 4. It does break into 8 and 4, but when you're looking for what to break it into, you really need to look for those perfect squares. Like when I say perfect squares, I mean 1, because square root of 1 is a whole number 1, 4, because the square root of 4 is 2, 9, because the square root of 9 is 3. So we want to break this into 16 times 2. And when you do that, we can actually separate it and we can solve 16. So sometimes you might see your answer as this. Now, if it is a calculator part of the test, then all you have to do is just punch this in the calculator I'll show you what that would look like. I can get my calculator back up here. 4 square root of 2. And you can see that there's the same answer that I just got a minute ago, 5.7. If it's not a calculator test, what you can also think about is this thing that came out from under the radical, we've taken the square root of it to get it out. So if you square it, 4 times 4 is 16, and multiply by this number in here, that's going to give you this original number. So that's another way to help you if you're having trouble trying to pick out this, if it's a not calculator answer. Okay, now the other big thing when you talk about the Pythagorean theorem, and this is something you might not know yet, but you can also tell me if I give you 3 numbers that make up a triangle, what kind of triangle it is. And what we typically do for that is we write the c squared first. So you're just going to have to reverse the formula. We're allowed to do that by the symmetric property. So if you put the 3 numbers in, now you're going to put the biggest number here, and it works out equal, it's a right triangle. If you put the numbers in and c squared is bigger than a squared and b squared, you're going to have, again, numbers here, then it's an obtuse triangle. So you can tell me what kind of triangle something is. If c squared is less than, that's the last case, we know it would be an acute triangle. So knowing about the Pythagorean theorem can not only help you find missing sides, but it can help you determine if something is a right triangle or not. Let's look at a couple of examples of that. Okay, so if I give you a triangle, again, even if they give you, I'm not even going to put these on a right triangle. I'm just going to list them out. If I say the square root of 13 and 7 and 8, and the question is going to say, what kind of triangle? Well, the first thing you're going to need to do here is, because the square root of 113, you probably already know it's bigger than those 2 numbers, but let's just verify that. So we're going to come over to our calculator and take the square root of 113. And it is, of course, bigger than 10. So that's our biggest number. So that's got to go in where c squared is, the square root of 113. I always tell my students to leave a box here, draw you a box here, because we don't know what symbol is going to go in here yet. And then it doesn't matter which one you put first for 7 squared and 8 squared. And this is going to be squared. Sorry, I left off the square part. All right. So as we keep going, these 2 things cancel out. So we're left with just 113 here. And let's just let our calculator compute the other. It can compute it in one step, 7 squared plus 8 squared. And the square button is right here on the calculator. But if it's the same button we used a minute ago for the square root, but if you don't hit the second, it'll punch the numbers in like I have on the screen. See how that's set? It's not square root anymore because I didn't use the blue button. So 7 squared plus 8 squared, that's going to be 113. Well, voila, I got 2 numbers that are equal. So if your number's equal like that, after you've done the math, then you can say it's a right triangle. So that would be a right triangle. Let's do another one. Let's do 11, 14, and 10. Again, the same question. Using this is called the converse of the Pythagorean theorem, by the way, because the Pythagorean theorem says, the 2 legs of the triangle squared, summed up, add to the hypotenuse. But this is saying that depending on how big c squared is, it's going to determine what kind of triangle this is. So we're not starting out with the right triangle. We're determining, is it a right triangle or not? That's the difference. The biggest number is 14. So we're going to put 14 first. Draw your little box. And then it doesn't matter which one you put in what spot for A or B. I'm just going to let my calculator work out the math of this. This is 196. Okay, 11 squared plus 10 squared is 221. So look what happened there. This number, and it's important, y'all, that you put the c squared first, or you're going to mess up these 2 symbols. This symbol would be less than. 196 is less than 221. So this would be an example of an acute triangle. Okay, guys, I hope you already knew a lot of the stuff about the Pythagorean theorem, but this last part about the converse of the Pythagorean theorem, it's pretty good stuff also to make sure you've worked some examples and got some understanding on. All right, everybody have a good day.